The eternal dance of creation. Look up at the night sky. It seems peaceful, quiet, almost frozen in time. Yet what you see, those tiny, shimmering points of light, are not still at all. They are alive. Each star is a raging sphere of fire, a living engine born out of chaos, burning for millions or even billions of years before fading back into darkness. And the space between them, which appears empty, is not empty at all. It's filled with invisible clouds of gas and dust, the ashes of ancient stars that once shone, died, and scattered their remains across the cosmos. It's here, in these cold and silent regions, that the next generation of stars is waiting to be born, the hidden architecture of the universe. For centuries, we looked at the stars and imagined them as eternal, but now we know they are part of an endless cycle of birth, life, and death. The universe is a massive recycling system. Stars create elements, explode, spread them out, and from those ashes, new stars rise again. If you could float in deep space, far from any galaxy, you'd see faint clouds of glowing gas stretching for light years in every direction. These are nebulae, vast, diffuse clouds made of hydrogen, helium, and cosmic dust. Some are so huge they could swallow thousands of solar systems. But despite their size, they are incredibly thin, so thin that a cubic centimeter of this gas might contain just a few atoms. Yet over millions of years, gravity begins to pull this scattered matter together, forming dense knots of gas, the seeds of future stars. The ingredients of stars. To understand how stars are born, we must first understand what they are made of. Roughly 75% of all normal matter in the universe is hydrogen, the simplest and most abundant element. Another 24% is helium. Everything else, oxygen, carbon, iron, gold, makes up less than 1%. But that tiny fraction is everything that makes the universe interesting. Planets, life, even us. Hydrogen and helium came into existence just minutes after the Big Bang, about 13.8 billion years ago. But heavier elements, the ones that form dust, rock, and metal, are the gifts of dying stars. When a massive star explodes in a supernova, it forges elements like iron, nickel, and gold in its core, then throws them into space. Those atoms drift through the galaxy until they find themselves trapped inside a new cloud, joining the next wave of stellar creation. So when we say that we are made of stardust, it's not poetry, it's chemistry. Every atom in your body was once part of a star that lived and died long before the Earth even existed. Gravity, the invisible sculptor. Now imagine one of those ancient clouds called a molecular cloud. It's vast and cold with temperatures just a few degrees above absolute zero. For millions of years, it drifts quietly through space. But gravity never sleeps. Tiny differences in density, small fluctuations where the gas is slightly thicker, begin to attract more material. And as more matter gathers, gravity strengthens, pulling in even more. This is a runaway process. The cloud begins to collapse. Inside the collapsing cloud, regions of higher density start to form. We call them protostellar cores. Each one is a potential star in the making. The gas falls inward, compressing, spinning faster as it shrinks, like a figure skater pulling in their arms. As it spins, it flattens into a disk, the beginnings of a solar system. At the center, pressure and temperature begin to rise. When the temperature in the core reaches about 10 million degrees Kelvin, hydrogen atoms begin to fuse into helium. This is the moment of ignition, the birth of a star. From darkness to light. For the first few million years, the newborn star, and called a protostar, is hidden within its cocoon of gas and dust. If you could somehow peer inside, you'd see something spectacular, a ball of superheated plasma glowing faintly red, surrounded by swirling material that will eventually form planets. Jets of gas shoot out from its poles, twin beams of matter traveling at hundreds of kilometers per second. These jets clear away the surrounding cloud like a baby pushing away its blanket, revealing the star to the universe for the first time. At that moment, the star begins to shine. Its light pushes outward, balancing the inward pull of gravity. The war between collapse and expansion ends in a delicate equilibrium, a balance that will last for millions or billions of years. From the ashes of dead stars, a new sun is born. The cosmic nursery. One of the most beautiful examples of this process can be seen in the Orion Nebula. It's a giant cloud about 1,300 light-years away, visible even to the naked eye in the constellation of Orion. Inside, hundreds of new stars are forming right now. Telescopes like Hubble and the James Webb Space Telescope have captured breathtaking images of this region, towering pillars of gas glowing with infrared light, hiding baby stars in their depths. If you could stand on a planet inside that nebula, though it would likely not be solid enough yet, the sky above you would glow in shades of purple, gold, and crimson. The light of newborn stars would shimmer through the gas, creating a scene so magnificent that words fail to describe it. These are the cradles of creation, the places where every sun, every planet, every life form begins. Part 2. The Lives of Stars: Youth, Adulthood, and Death. Once a star is born, it enters the longest and most stable phase of its life, the main sequence. This is the cosmic equivalent of adulthood, balanced, bright, and productive. The star fuses hydrogen into helium in its core, releasing light and heat. This nuclear fusion is what makes the sun shine, and every sunrise on Earth is powered by the same process that has been burning for 4.6 billion years. The cosmic family. Not all stars are alike. Their size determines everything: their color, brightness, lifetime, and even how they die. Red dwarfs are the smallest, dim, cool, and incredibly long-lived. They burn their fuel so slowly that they can survive for trillions of years, far longer than the current age of the universe. If the cosmos were a forest, red dwarfs would be the quiet mosses covering the ground, humble but eternal. Sun-like stars live comfortable, middle-aged lives, billions of years of steady light. They are yellow-white, warm, and stable enough to host planets with life. Our own sun has burned halfway through its fuel. It's in its peaceful prime. Blue giants, on the other hand, are the rock stars of the cosmos. Massive, brilliant, and short-lived, they shine millions of times brighter than the sun, but burn out within a few million years. They live fast and die young, leaving behind spectacular remnants. The bigger a star is, the shorter its life. Gravity and pressure wage a constant war inside it, and the more massive the star, the faster that battle consumes its heart. The heartbeat of a star. Inside every star, fusion is a battle between two titanic forces. Gravity tries to crush the star inward, pulling all its matter toward the core. Fusion, on the other hand, pushes outward. As hydrogen atoms slam together, they release enormous energy. That energy creates pressure that balances gravity's pull. This fragile equilibrium is what keeps a star stable. But it cannot last forever. When the hydrogen in the core is exhausted, Fusion slows down. The star begins to change, and its life enters the final act, the red giant phase. For stars like our Sun, the next stage is dramatic. When hydrogen runs out in the core, gravity takes the upper hand. The core contracts and heats up while the outer layers expand outward. The star swells to hundreds of times its original size, becoming a red giant. If our Sun followed this path today, its outer edge would extend far enough to swallow Mercury and Venus, and possibly Earth. The once yellow star would glow deep red, enormous and beautiful, but unstable. Inside, new types of fusion begin. Helium atoms fuse into carbon and oxygen, creating the elements that will later become the building blocks of life. For a short while, the star finds a new balance, but it won't last long. The death of a sun-like star. Eventually, even helium runs out. Without fuel, fusion ceases. The outer layers drift away into space, forming a glowing shell of gas, a planetary nebula. Don't be misled by the name. It has nothing to do with planets. The term was coined centuries ago by astronomers who saw round, planet-like shapes through early telescopes. At the center of this expanding cloud remains the star's core, a small, dense ember called a white dwarf. It's roughly the size of Earth, but contains nearly the mass of the Sun. It no longer produces energy. It simply glows from residual heat, slowly cooling over billions of years until it becomes a black dwarf, a cold, dark corpse of a once shining sun. One day, our own Sun will follow this exact path. The atoms that make up you and me will drift into space, perhaps to become part of new stars, new planets, and new lives. When giants die, massive stars, those 8 times heavier than our Sun, meet a far more violent fate. When their fuel is gone, gravity crushes the core with unstoppable force. The collapse is so sudden that it triggers one of the most powerful explosions in the universe, a supernova. In less than a second, the star's outer layers are blown away at a speed of tens of thousands of kilometers per second. The light of a single supernova can outshine an entire galaxy. If one occurred a few light years from Earth, it would cast shadows on the ground even at midnight. During these cataclysmic moments, nature's greatest alchemy takes place. In the heart of a supernova, the elements heavier than iron, gold, silver, uranium, are forged. Every ring, every piece of metal, every drop of blood containing iron owes its existence to such cosmic deaths. Supernovae are the universe's way of renewing itself. Destruction creates the materials for creation. Neutron stars and black holes. When the explosion fades, what remains is the collapsed core. If the original star was moderately massive, the pressure of gravity squeezes protons and electrons together into neutrons, forming a neutron star, an object so dense that a teaspoon of its matter would weigh billions of tons. Neutron stars can spin hundreds of times per second, emitting beams of radiation that sweep through space like lighthouse beams. When those beams cross our line of sight, we see pulses of light. We call these stars pulsars. But if the original star was even larger, more than 20 times the mass of the Sun, gravity wins completely. Nothing can resist its pull. The core collapses into a black hole, a point of infinite density where space and time themselves are torn apart. From the outside, the black hole appears as a region from which nothing, not even light, can escape. Yet it doesn't merely devour. It also shapes galaxies, bends light, and may even seed new stars around it through the turbulence it creates. In the end, Black holes are both destroyers and sculptors, the dark hearts of galaxies that keep the cosmic ecosystem in balance. The circle never ends. Every generation of stars leaves behind matter that becomes the seed of the next. The carbon in your lungs, the calcium in your bones, the iron in your blood, all were born in the hearts of stars that exploded billions of years ago. When you look at the Milky Way, you are not just seeing distant sun. You are seeing your own ancestry. Stars are storytellers written in light. Each one is a chapter in the long, endless book of the universe. A story that began with dust and ends with life. Part 3. Supernovae, Cosmic Recycling Machines and From Ashes to Creation. Imagine a star nearing its end. Its light flickers. Its core grows heavy with iron, an element that cannot provide energy through fusion. The balance that once held the star together begins to fail. And then, in a final heartbeat, gravity wins. The core collapses inward at a quarter of the speed of light. In that instant, the outer layers rebound off the compressed core and explode outward in a blinding wave of energy, a supernova, a death that gives life. A supernova is not just an explosion, it's a rebirth. In the span of a few seconds, temperatures reach hundreds of billions of degrees. New atoms are forged in this furnace of chaos. Gold, platinum, iodine, uranium. These elements rush out into space, mixing with interstellar gas, drifting through galaxies, waiting for billions of years to become part of something new. Without supernovae, there would be no planets, no oceans, no living beings. Every sparkle in your jewelry, every drop of blood in your veins carries the memory of such an explosion. So when a star dies, it doesn't truly vanish. It transforms, scattering the ingredients of future worlds across the cosmos. The seeds of new worlds. Over time, these remnants, gas, dust, and heavy elements, drift and mix in the galactic disk. Eventually, gravity begins to gather them again into new clouds. The process that once destroyed a star now helps to create new ones. In regions like the Eagle Nebula, telescopes reveal towering columns of gas, the famous pillars of creation. Each pillar is light years tall, sculpted by radiation from nearby massive stars. Inside these dark, dense fingers of dust, new suns are forming, hidden from sight. It's a breathtaking image of cosmic continuity. Creation, born from destruction. The same elements that once burned inside ancient giants are now coalescing into new worlds, perhaps even worlds like ours.